Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. We are studying Chapter 3 of the Dahm and Visco Thermodynamics textbook on material and energy balances, and we're looking at examples of steady flow processes and the energy balance necessary for those. As a reminder, we've developed an energy balance, a general form shown here, that uses enthalpy for the flowing stream's total energy. Recall that this combines the internal energy U with the flow work PV. And so we have the rate of accumulation is the difference between the flowing energy in and out, plus the shaft work and the expansion and contraction work and the heat transfer. But for our steady flow processes, we have developed some formula. The material balance, when you do not have an accumulation component, is that the mass flowing in is equal to the mass flowing out via all streams. And our energy balance for a steady flow process with no accumulation is that the rate of heat transfer plus the shaft work, or the power, W dot is really power, is equal to the sum of the total flow enthalpy or flow energy out minus the sum of the total flow energy in. Now that flow energy is enthalpy plus 1/2 the velocity squared plus GZE. So that's our internal energy, kinetic energy, and potential energy plus the PV work that makes the flow happen. Just another view of that equation with the two sides switched, but otherwise it's the same equation. This is an equation that, although you can have it written down, I would commit this to memory. It's going to make your work quicker if you have this committed to memory. Let's look at an example of a nozzle. Now, in this case, a nozzle is expanding CO2 from 500 Kelvin and 1 megapascal to 440 Kelvin and 0.5 megapascals. The process is adiabatic, and CO2 with a molecular weight of 44 may be considered to be an ideal gas. If the inlet velocity is small, determine the exit velocity. And then there's data from the appendix, which says that C sub P over R is this function of temperature for temperature in Kelvin. My recommendation when you work a problem like this, all of our problems are going to be story problems of this sort. They're long and complicated, so I recommend beginning by rewriting the problem statement with symbols, okay? So we're going to have CO2 as an ideal gas, and we have a nozzle. We'll discuss that in a moment. We have the inlet temperature is 500 Kelvin. The inlet pressure is 1 megapascal. Now, based on what I said in previous lessons, it's really helpful to go ahead and, do this in kilopascals. So 1 megapascal is 1,000 kilopascals. You don't have to do that, but it will just make the rest of your work quicker. And then we have the exit temperature is 440 Kelvin. And the exit pressure, again, converting this to kilopascals, is 500 kilopascals. The process is adiabatic, tells me that Q is equal to 0. The molecular weight of the gas is 44. The inlet velocity is small. Okay. When they say the inlet velocity is small, what they are trying to tell you is it's so small that you can ignore it. we will call it essentially zero. Now, we are asked to find the exit velocity. And I usually draw a little arrow on velocity just to make sure I know it's velocity and not volume, because it's a little hard to tell whether you wrote it small or large, right, for upper and lower case. Once I've rewritten the problem statement in symbols, like I've done here, the next thing I generally do is do what I can to simplify the first law. So now, if I need a material balance, I would also do that and simplify it. But here, mass in equals mass out, so material balance isn't very interesting. But let's write out the general form of the first law for a system with flow. I am writing this for one stream in and one stream out, so I'll drop the summation signs. But otherwise, I've left everything in. And now we want to look at what we know. Q is assumed to be 0, and VI is assumed to be 0, and what we can assume. So let's make a note of what we are assuming. So I will assume, well, what else? Really, the only other thing that I see here is that ZE and ZI are probably very close to 0. So what that's telling me is that there's not much of a height change. Now let's think about a nozzle. A nozzle can either expand or contract stuff, but basically it's like a small section of pipe, essentially, that goes from a large diameter to a small diameter, or the converse of that, starting small and going large. You'll see these like on the bottom of a lot of rockets, okay? They'll have an expansion section there. I use one when I'm trying to do a sprayer because I'm too lazy to add an extra piece of hose, and to get to the back corner of my yard, I have to use a sprayer to be able to reach that far. I could also add another section of hose, but I'd rather not. That sounds like too much effort. So the purpose of these devices is to basically change the velocity so that the material will go further, right? It either adds or subtracts kinetic energy from the system. So if you think about how those are built, typically the change is very small. And I wrote that as ZI equals 0. I meant to say ZI is equal to ZE, or delta Z is equal to 0. Any change you'd have would be very small. And if you were to put in some height differences you might see in a typical nozzle, even for something as large as a rocket, with the CO2 here, you're going to find that really the numbers don't change as a result of that. All right, so we've gotten rid of those. My simplified equation, therefore, says that power is the mass flow rate times HE plus 1/2 VE squared minus HI. Okay, we're almost there, but if you read this, okay, there are several things going on here. First of all, they didn't tell me anything that's going to give me a hint what the mass flow rate is. And what's the power of a nozzle? Okay, again, this comes from, think about an easy way to make a nozzle, right, is to take the garden hose and put your thumb in front of it, reducing the area. Okay. Are there any moving parts there? No. Okay. Work always requires movement. So if there are no moving parts, I can also assume that the power is going to be 0. Therefore, this simplifies this one last little bit. That goes away. And I'm trying to find the exit velocity. So let's write it in terms of velocity equals If you do the algebra properly, then you find that the velocity is the square root of 2 times the specific inlet out enthalpy minus the specific outlet enthalpy. All right. We have C sub P. I don't have a steam table for CO2, but recall that we have said earlier that delta H is the integral of C sub P dt with an equal sign in there. So delta H is going to be the integral of C sub P dt. So really what this is saying is that V sub E is going to be the square root of 2 times the integral from the exit temperature to the inlet temperature of C sub P dt. Now we have this expression up here for C sub P over R. So C sub P is going to be this expression times R with your choice of units. But I need to integrate that with respect to temperature. Don't just evaluate it and then say times delta T. C sub P is changing with temperature in a fairly complex way, correct? So therefore, I want to do the integration. If one integrates this polynomial, because really that's all it is, you get 2 times R, that comes from the fact that it was defined as C sub P over R, times the first constant times Ti minus Te, 1/2 the second constant Ti squared minus Te squared, plus 1/3 the third constant Ti cubed minus Te cubed, 1/4 the fourth constant Ti to the fourth minus Te to the fourth, plus 1/5 the final constant Ti to the fifth minus Te to the fifth. Right? Now all we need to do is plug numbers in and we can calculate this. It says to do T in Kelvin. That was part of the instructions. And if I do that, using my calculator, I found that that whole integral mess from Ti of 500, or actually I have my I's and my E's switched all the way through. I am so sorry. 440 to 500 with all of those I's and E's switched. I end up with 315.81. Now the units on this, remember it was C sub P dt that we were getting this from. And the C sub P is going to get its units from R, and dt has units of Kelvin. So this so far has units of Kelvin, but I haven't plugged in a choice for R yet. Now you can use any choice for R. That's where I'm going to get the units for the answer. But let's use the most common one. Let's use 8.31447 cubic meters, kilopascals per kilomole Kelvin. Okay. Now, first of all, kilomoles. I know that I want this to be, everything else is given, they gave us the molecular weight. Everything I know has been done in kilograms. You remember we have that unit conversion, 1,000 meters squared per second squared is a kilojoule per kilogram. Everything's been in kilograms. So let's take the hint that they gave us. 1 kilomole is 44.01 kilograms. If you don't do that now, it's not the end of the world. It just, I'm going to want to, as quickly as possible, get rid of the kilomoles and move to kilograms. Okay, but now I still have garbage units, right? This is meters cubed times kilopascals per kilogram. Those kelvins there canceled also. Okay, that's garbage units. When I take the square root of it, I'm going to be even more confused. So what I need to do I can evaluate this so far with my calculator, but the units are meters cubed, kilopascal per kilogram. And now then, I know that a kilojoule is the same as a cubic meter kilopascal, and 1,000 meters squared per second squared is 1 kilojoule per kilogram. Now, I know to go through these steps because I've worked with these units for a long time. This is something that you will get used to, but if not, if this isn't something that's easy for you, just go ahead and write it down. Put a note somewhere that this is how you do this unit conversion, and you'll get to the right answer without having to put in terribly much thought. But okay, so the meters cubed per kilopascal cancels. I have a kilojoule per kilogram, which is going to cancel with this kilojoule per kilogram, leaving me with meters squared per second squared. When I take the square root, I'll get meters per second. So here I am, I'm multiplying by 1,000. In the previous lesson, in our pump problem, we had a place where we divided by 1,000. This is so important because if you don't remember to do this unit conversion, you're going to end up with garbage answers. So the velocity at the exit is going to be the square root of 119,330 meters squared per second squared. Take the square root of that, 345 meters per second. Okay. Now, a couple of different notes here on this problem. First of all, we're going to have to work with C sub p as a function of t a lot, and it's almost always this polynomial function. Create yourself like an Excel file or something like that to do this integration. It will make your future just that little bit easier. All you'd have to do is enter in the choices of those constants, A, B, C, D, etc. And if you have something where maybe there isn't a fifth term, great, you put in 0 for that constant. Excel would still be able to do the work for you. Second, pay really close attention to the units. Anytime you have velocity or height, pay attention to the units. And our best friend here is that 1,000 meters squared per second squared is equal to 1 kilojoule per kilogram. Okay. And I guess then my final thing is that when you are doing the integral of C sub p dt, it is not the same as saying C sub p times delta p. This is one of the places that people frequently make mistakes. I guess the last place that people make mistakes before I move on is that don't forget to do the square root. At the end, when you're doing the calculations, I've so often seen people, they wrote it down, they just, when they gave their final answer, they forgot to do it. This concludes this example. This was a nozzle problem, and we're going to continue the study of steady flow processes and look at other examples in our next video lessons. Thank you very much for your time.